I'm Fabio. I work for a company called Logical Clocks. We are based in Stockholm, Sweden, and we created Ops. And today I'm going to talk about how you can run distributed TensorFlow on the Ops platform. So one of the motivation why I became interested into the deep learning space is because, like, nowadays, if you want to succeed in solving problem with deep learning, the key component is data, basically. And these are two sections of two different papers of two different groups looking into the same issue of, like, how do I improve my model performance? And both of them reach the same conclusion of, like, just throw more data to your model. And you have, like, a huge window of opportunity when you can basically improve performance by having more data to train on. And while you do that, two problems come up. One is that you need to store all this data, you need to access it really fast, and then the second one is that you cannot train anymore on your laptop, but you need to scale on multiple workers and multiple machines. So I'm going to address these two problems in the rest of this presentation. Starting with like how to store all this data, the key element of the Ops platform is the file system. It's called OpsFS. It's a fork of Apache HFS. The idea here is that we change the way that metadata for files directory actually managed, and we move them from the name node memory to a distributed in-memory database. And this allows us to have multiple active name nodes, and we can redistribute the clients across all the name nodes, achieving, like, higher throughput, like 16 times more throughput than HFS, and a larger file system because we are not limited by the memory of the machine when the name node is running anymore. Important point here is that TensorFlow has support for reading and writing to HFS. We didn't break the client API, so we basically you can basically run TensorFlow and read and write from OpsFS without any modification required. The second change we made was how small files are actually handled in the platform. And this is actually important for deep learning scenarios. In HFS, small files are problematic for many two reasons. The first reason is an internal reason of, like, how communication happens between the name nodes and the data nodes. The second reason is from a client perspective. If you want to read a small file, you still need to access it and establish secure connections, increase the latency. So what we do is in OpsFS is basically we package the file content together with the metadata. So you have only one connection to open to read both the metadata and the file content. We run some benchmarks on the open image dataset, which is that's maintained by Google. So around like 9 million images. 80% of them are within our definition of small files, so less than 64 kilobytes. It takes around 2 minutes to read the whole data set, and you're basically reading something around like 75,000 images per second. The third thing that actually we modify and we separate ourselves from the Hadoop, like all the other Hadoop distribution, is how we handle security. If you're familiar with Hadoop, you know that the security is dedicated to Kerberos. We got rid of Kerberos, and we put in place a security model based on X509 certificates. The life on the platform is organized in projects. Think about sort of GitHub projects. I can collaborate on multiple projects, and for each project, I have a different certificate. When I start a job on application, another certificate for that specific application is actually generated, and I use that specific application certificate to access the file system, to access the data, and the file system records which file I read, which file I wrote, and created, and so on and so forth. As I said, on top of that, we built, like, a standard big data platform with all the tools you need for instance, ingesting data through Kafka, pre-processing, Spark. But today, we're going to focus mainly on Jupyter, PySpark, and TensorFlow. So going towards, like, distributing the computation, the first thing, if you are a data scientist, you want to work on, model problems and not bother with, all the DevOps stuff. So the main things, the first thing you do when you are tackling a problem is, building and experimenting with different models architecture, different hyperparameter setup, and so on and so forth. And it's kind of boring because you have like maybe 100 experiments. 90 of them do not lead to a good result. 10 of them needs more investigation. So you run even more experiments. And the thing is, this thing needs to be automated and can be automated. That's why we develop a library called the Ops Python library. The idea is that you write your code into a Jupyter notebook, and you write your code in a way that you wrap your code in a function, and you write this function in a way that you can inject hyperparameters, different hyperparameters value at runtime. And I have an example afterwards, so we can see how it works. And then you call the library. And the idea is that we use Spark in this case to do resource allocation and code distribution. The library will start n Spark executor, depending on how many experiments you want to run. In Ops, we have support for scheduling of GPU resources. So executors can have one or multiple GPUs. And you run basically the experiments. While you're running experiments, as we see later in the demo, you have access to the tensor board, so you can see how the training is going. We have 3 modes to run this library. The one is basic mode, and basically saying, OK, I want to test my model on like these 6 different values for dropout values and 6 different learning rates, and this starts 6 executors. Grid search, if you specify 6 values for dropouts and 6 values for learning rates, it will start 36 experiments. And finally, differential evolution, which is kind of nice. The idea is that here you define a box. You pick a random population within this box. You train on this population. You look at the performance of each model. The population is a combination of 5 parameters in the space you define in the box. You apply some crossover and mutations, and then you repeat the steps several times until, as you can see, do we have a mouse? Yes. Until generation 10, you can see basically all the elements in the population leads to good results. I do have a demo. So this is the platform. As I said, the life is organized in projects. So I can go and set up my Jupyter notebook server. This is a small VM. I have only 2 GPUs on this one, so I can start it. This will start my Jupyter notebook server. Let's run an example, for instance. We have several examples in the demo tool, so you can play with it. So, OK, this is just documentation of what I'm saying right now. Can you see it? No, maybe I should increase it a bit. As I was saying, you wrap your code. OK, you don't have to write all the code inside this function. You can have like external modules and so on and so forth. The idea is that you pass the hyperparameters you want to test on. And basically, this is like standard TensorFlow code. This is like a classic Minster example. And this, again, at the end, the function returns what you want to optimize for. In this case, we want to optimize for accuracy. We define which kind of hyperparameters you want to test, and the values. As you can see, like a grid will be built. And finally, you call the libraries, and you pass this Spark environment, which is given to you automatically because we are running a PySpark kernel in Jupyter, the wrapper function, the dictionary, and the direction you want to optimize, or if in this case we want to optimize for for better accuracy. While it's training, we can see right now. OK, right now I have only 2 GPUs, so it's running 2 of them at the same time. It's loading dashboard 2. And yes, and this is how the training is going for this to experiment right now. Once it's done that, the library sends like a set of information to Elasticsearch that is deployed alongside with the platform. And we can track all the experiments we have run and what were the results and which hyperparameter combination was the best one. And in particular, if you pick, these are the samples I ran yesterday, I can pick one example, and it should show up the tensor board for that example. It's kind of overloaded right now, the machine. Maybe. Yes, eventually we come up. Yes, and here you can see that you have like basically all the different experiments in the same graph, eventually, yes. And down here you can basically say, okay, show me only the one with the, I don't know, learning rate. 0.1, and it filters them with the regular expressions, basically. So coming back to presentation. So as I was saying, we track a series of stuff regarding your experiments. One is the results itself. Second one is the parameters, the space you were training on and you were experimenting on. We took a snapshot of the Jupyter notebook you run. So if you can come back like in a couple of weeks and say, okay, I want to retrain on the same notebook. I didn't mention this. Each project has its own Conda environment. So you can basically either using the Conda package manager or pip, you can basically install all the Python libraries you can think of, and they are publicly available. So we take a snapshot also of the current Conda environment, and we are working on also taking a snapshot of the dataset itself. So once you are happy with your model and parameter settings, time to like move on to training on the real model. If you have big data, as I hope you do, you need to scale on multiple GPUs and multiple machines. If you use TensorFlow, TensorFlow has a really nice APIs called TF estimators. They are really nice. They add away a lot of complexity and makes your code really readable. The idea is if you're running by hand, you basically start multiple processes, and you basically export this TF config environmental variable, which describes where your workers are, the parameter servers, where they are, and on which port they are listening on. If you run distributed TensorFlow, there are two architectures. One is the parameter server architectures, and the other one is the ring or reduce. Starting from a parameter server architecture is the most well-known, I would say. If you are looking at like tutorials online, 99% of the time you will see TensorFlow parameter server architecture. The idea is that you have two types of workers. One is the parameter server, keeping track of the weights across the training, and the second one is the workers. Each worker gets like a slice of data, train on that slice of data, and sends to the parameter server the graded updates. Parameter server aggregates all of them and sends them back to the worker for a new iteration. In ops, again, we use Spark, and we use in particular a tool called TensorFlow Spark, which was open sourced by Yahoo. And we use Spark again for resource allocation and code distribution. And the library itself manages a tensor board again, so you don't have to do anything. You will see a tensor board of showing up to show the training how it's going. I don't spend much time on this, and you will see later why. This is how you convert you do the conversion, and basically you have your TF cluster.run. Again, in the Spark context, your training function, number of executors or number of workers, number of parameter server, and then the training function itself, you call this start cluster server, which gives you back an object telling you, okay, are you a parameter server on that specific process, or are you a worker? I don't spend much time on this because in reality, if you are really trying to scale out your training, the parameter server architecture doesn't really scale. This is our internal experiments we run. On the left side, we have the parameter server architecture. On this side, we have I should have written like, the reduce. You don't really probably see. Text is too small, but. The green line, the straight green line is the ideal scaling and speed up. So the idea is that if you have twice the number of GPUs, you will be basically processing twice the number of images. As you can see, on the left, on your right side, so on the parameter server one, you have basically pretty much flat, no matter how many GPUs, how many workers you add. This doesn't really come closer to what's the ideal speed up. On this side, on your left side, you have the reduced architecture, as you can see, except for do example below there, pretty much everyone, all the other models are basically following what's the ideal speed up. And the reason for these two models down here is that because after we ran the experiments, we noticed that there was a network configuration in our setup problem, network problem configuration. And yeah, otherwise they would be like kind of following the same pattern. So why is this different? The idea is that when you're using parameter server architecture, the network to get the parameter server and the parameter server become the bottleneck. So in the all-reduced architecture, what you basically do is like you throw away the parameter server and you organize your workers in a ring. And each worker communicates with the next one and receives data from the previous one. Now, to communicate, to transfer like the gradient updates, they use a communication pattern called O-reduce. The idea is that you basically have like a chunk of information, the buffer of information you want to send, you chunk it up, and you do a series of iterations, and at each iteration, you basically send one chunk and receive one from the previous one, and while you're receiving, you do like an operation, in this case aggregation, and then you send it back to the next one. And you do this for, well, two n-1 iterations, and that's it. In ops, we use a library called Autobot, which was open sourced by Yahoo. The idea is Autobot is built on top of the NVIDIA SCCL2, which is the NVIDIA collective communication library, which provides implementation for this all-reduce communication pattern. The library also provides an interesting feature, which is basically allows interleaving of communication and computation. So while you're training a model and you are backpropagating the error, especially in deep models, the gradient updates for the outermost layers are available much earlier than the one in the innermost layer. So you can start transmitting, so you start doing the communicating and doing the all-reduce communication pattern while you are still backpropagating the error. And you can see this in these two experiments we ran. On your left side, you have Autobot. As you can see, during the experiment, this is the GPU utilization. It basically spikes up around 90% and stays pretty much flat throughout the whole experiment. While for the parameter server, it's really spiky in the sense of like, okay, you have computation, transfer of gradients, computation again, and you have all these spikes. And if you average the GPU utilization, you're probably around 40–45%, which is pretty bad. We also, in ops, have support for a multi-machine Autobot. Again, we use Spark for the resource allocation. We allocate containers in your Yarn cluster, and we collect information on which machine and which devices they're being assigned to, and we send everything to this component we wrote, which is the MPI wrapper, which takes care of actually starting the process with the correct configuration and monitoring that you are not using more GPUs or more resources than what you have been assigned to. This is how you run it, Autobots. I do have a notebook to show. Let's pick this one. So, okay, we have a bunch of documentation again here. Two things are important here. One thing is you have to do a little bit of initialization. Again, this is way probably too small. You have to do a little bit of initialization. And then what you basically do is you feed your TensorFlow optimizer, whatever optimizer you're using, and into this Autobot distributed optimizer. And this takes care of actually setting up all the communications and doing basically all the magic behind the scenes, basically. And yeah, the rest is basically TensorFlow code, except yeah, you have some initialization for the weights in the different processes, basically. Oh yeah, sure. Also, okay, this is a notebook to actually write everything, and then we have a separate notebook to actually launch the training itself. Again, we have a wrapper for the ops library provides easy access to start the Autobot training. You just have to pass your Spark context, and you pass the path to the notebook. This is the path on HFS for the notebook itself. So finally, in the last stage of your model lifespan, you have model serving. And in ops, we are basically aligned with what the rest of the community is doing, of basically using Kubernetes for managing the managing the Docker containers running the TensorFlow serving instance. We do that because Kubernetes honestly provides a lot of already tools to do fault tolerance, releasing of new models, being online without any downtime. Provides easy way of doing auto-scaling. If you get a spike in requests, you can basically spin up new images and serve more traffic. The idea is that here we use OpsWorks, which is the UI I was showing before, as an entry point for your request. And OpsWorks take care of, you can have private models, and it takes care of authenticating the requests coming in, and otherwise just forward them to your inference cluster or running over Kubernetes. Sadly, though, this is not the end of the story. While you're actually serving models in production, I think it's been repeated in the previous two talks quite a lot. You need to monitor that your model is actually behaving correctly. And the thing is, while you're running, it's not that the model fails only throwing you a 404 or 500 error, whatever HTTP error it throws you. It can also start serving you bad inference. So if you train one of the reasons this happens is that you train your models on a different distribution of the data of the data which is coming in. So for instance, you train your model of 98% of cats and 2% of dogs, and then suddenly all the requests are for dogs, probably your model won't work. So we built also a separate section here for monitoring that what is actually coming in matches the same distribution of the data of what your model trained on. So when a request comes in, it gets forwarded to your Kubernetes cluster for inference, but it also gets recorded to either Elasticsearch or into a Kafka topic. And if you send it to Elasticsearch and you have easy access to Kibana for visualization, if you send it to a Kafka topic, then it's easy to, from a Spark application, either a Spark streaming application or a Spark application that runs every now and then, to read the data, compute the distribution of data, check that the distribution matches the one that you actually train on. If it doesn't match, REST request to REST call to OpsWorks, train again the same model, and if it's OK, validate it, and then if it is OK, start serving it in production. The second reason we do that is because while you are ingesting data from the clients, this data becomes really valuable for training new models. So what you basically do is that you basically sync all the requests into persistent storage like OpsFS. That was all basically what the platform offers, from building up the model to actually serving into production. The documentation on what I was talking today is on ops.io. The platform itself is open source. You can go on github.com/opshadoop, leave a star, or open a pull request if you feel like. And this is our Twitter handle, so that's pretty much it.
We have time for a question or two, if anyone wants to.
Yeah.
So when you talk about scaling out reduce with distributed training,
Yep.
One of the problems is the network between the instances, which many times requires you to have a dedicated cluster.
Yep.
How do you guys solve that problem?
Well, the idea is that in Yarn you support node labeling. So the idea is that you can request for a set of machines which are connecting us. Maybe this set of machines they do have InfiniBand connection, for instance, and the rest of the machine maybe do have only Ethernet connections. So you can label this machine particularly and ask explicitly in your request for this set of machines. So they are connected to a high-speed network, and that's the way we do it basically.
Right. Thank you very much.
Thank you.